Okay, great. It's a pleasure to have Melissa Sugimoto tell us about decompositions and glueings of locally integral involutive residuated structures. Please.
Okay, well, good afternoon, everyone. Thanks for having me here. As previously stated, I will be talking about decompositions and glueings of whatever these locally integral involuted residuated structures are. An alternative title of this talk could be, What Have I Been Doing for the Past Few Months? That is theoretically justifying my place here as a graduate student. And this is more or less going to summarize sort of the main results that we found over the past several months since I arrived here at Chapman. And in order to get into that, I will have to double click on the screen so that I can get out of Zoom mode. There we go. In order to get into that, we're going to start with residuated lattices. So this was our original sort of motivation. We know that residuated lattices are important in things such as substructural. Well, they are the algebraic semantics of substructural logic, that sort of thing. And this property of integrality that we're going to be looking at, which is that the top element is the global identity, is also equivalent to the proof theoretic property of weakening. So from this perspective, it's useful to study residuated lattices, it's useful to study integrality, but this isn't quite what I'm studying. So we'll see how we get from residuated lattices into and integral things into locally integral, involutive, partially ordered semigroups. And we start at the beginning, which is with the residuated lattices. When we say a residuated lattice, and I hate to sound like a broken record for a lot of the people here, a residuated lattice is a structure of the following form. We have a meet and a join that form a lattice. We have a multiplication with an identity forming a monoid, so it's also associative. And then we have these two binary operations, left and right division. And they have to satisfy this residuation property, namely that x times y is smaller than z if and only if y is smaller than x under z, or equivalently, x is smaller than z over y. And from there, we can begin to generalize, because this is one of the main things one likes to do, just go more general. And we could say that we have a residuated poset instead, drop the requirement that things be lattice-ordered and say they just need to be partially ordered, but let's keep everything else the same. So now we just got a partially ordered set, a monoid, and those left and right residuals that still satisfy the same property. And we can note that, all meet and join free redux of residuated lattices are going to be residuated posets, but there are also plenty of residuated posets that do not come from lattices. And then we take another step from there, and we do two things in this step, so it's really kind of two steps at once. And this is where I introduce the objects that we've been studying lately. We call them involutive partially ordered semigroups, or because that's a mouthful, just ipo-semigroups. And they're structures of a little bit of a different form. We still have a partially ordered set attached, but now we have a binary operation that does not necessarily have an identity, only needs to be associative. And instead of those left and right residuals, we have two order reversing unary operations, we call them tilde and minus, and they satisfy two properties. The first property is called double negation, which is that tilde minus x is equal to x, or it's also equal to minus tilde x. So applying minus after tilde and tilde after minus cancel each other out. And then the second property that we've got to satisfy here is called rotation, which is called such because we can essentially rotate the elements around x, y, and z, around the inequality, by applying these unary negations, which is to say that x times y is less than z, if and only if minus z times x is less than or equal to minus y, or equivalently, y times tilde z is less than or equal to tilde x. And the cool thing about this, the reason this is related to the residuated things we're just talking about on the previous slides, were that in the presence of these order reversal in our unary operations and the property of double negation, this rotation property is exactly equivalent to this residuation property that I've written here below, or we express something, once again, that expresses equivalent conditions of x times y is less than z, but in terms of these unary operations. And in fact, if we have this, then the residuals, the left and right residuals that we had previously, are term definable using this setup by saying that z over y is exactly equal to minus y times tilde z, and x under z is equal to tilde of minus z times x. And so if we rewrite the residuation property from the previous slide in this new notation, or really this old notation, it comes out to be exactly the same thing as the residuation property that we were requiring when we defined residuated lattices and residuated cosets. And so what we get out of this is that every unital ipo-semigroup, so every ipo-semigroup that has a global identity, is also going to be a residuated coset. And that's how we sort of go back from the things we're working with to the things we started with.
And that goes the other way as well, right? If you have a unit, then I can define the two negations.
I don't know. It doesn't necessarily go the other way around, because you may have residuation, but you will not be guaranteed involution. There are definitely residuated things that are not involutive.
That's because it depends on the unit's position in the structure. That's true. That makes sense.
Speaking of those units, or having an identity, we then just say, well, if an ipo-semigroup A has an identity, the semigroup is a monoid, we'll call these ipo-monoids. There's a little bit of a technical thing here where you determine whether or not you want to include the one in the signature, but we sort of just refer to these all as the same thing. If it has an identity, we're going to call it a monoid. And that is to say, from what we learned on the previous slide, the ipo-monoids are exactly the involutive residuated cosets. And here's where we get to the concept of integrality. Now that we have an identity again, we can say, well, if that's the top element, then A is integral. That's just our definition. And all elements are smaller than 1. We can also then, because we have involution, talk about what the term minus 1 can be. And minus 1 will turn out by some calculation to be the same as tilde 1, and we'll just call this element 0. And we'll note that since tilde and minus are order reversing, we could, if we wanted, express integrality by saying everything is bigger than 0. So when we have an integral involuted thing, we are both top and bottom bounded by 1 and 0. But I didn't say integral ipo-semigroups, I said the locally integral ipo-semigroups. So our goal here is going to be, first off, to try to generalize this concept of integrality in a way that's going to work for us in our setting. And to that end, we want to talk about what's called local identities. If we're in the setup where we have these left and right residuals defined from our involutions, and we get that x under x is always equal to x over x for all x, and we get one more thing, that x times this term is again x, well then this term is sort of acting as an identity for x. You multiply it by x and x stays there. So we call that a local identity. And to be more compact and to also be suggestive of identities, we call the term x over x 1x. And then we can define a term called 0x just by taking the minus of that again. So this is having local identities. This isn't quite what we're talking about when we say we want something that's locally integral. So we define locally integral by adding a few more conditions. We say that our ipo-semigroup is going to be locally integral if, of course, it is an ipo-semigroup. We also want it to have those local identities, so those elements that look, if you zoom in on small pieces, like they are identities. And then we want these local identities to satisfy a couple properties. Namely, we want them to be positive, so multiplication by a local identity makes things bigger. And we want the elements to be bounded by their local identities, which is to say x is smaller than the local identity 1x. Third thing that needs to fall out of this is that x under 1x is again equal to 1x. If we satisfy all these three things, this is what we call locally integral. And if we look at something locally integral, zoom in on a small piece, it'll look sort of like something that is then bounded by the local identity 1x and on the top and 0x on the bottom. See that in a second, I think. And to make sure this is really a proper generalization, we also confirm that every integral ipo-monoid is also locally integral. So everything that is integral is locally integral, but then there may be some more things that are just locally integral and not integral. We also have this equivalent way of characterizing local integrality, and this is actually the characterization we came up with first, and then came up with the one on the previous slide and thought that worked a little better as a cleaner definition. But what we came up with first is that we could also say that things are locally integral, and by things I mean ipo-semigroups, if and only if they satisfy these four conditions here. One, that minus x times x is equal to x times tilde x, which is very similar but not quite the same as saying that x over x and x under x are equal to each other. And second, that x over x, we still want that to be a positive term, which is that things get bigger when you multiply by it. And thirdly, we want multiplication to be square decreasing, which is x times x is smaller than x. And finally, the term 0x, we want all of those to be idempotent. And if we have all four of those things, this is exactly equivalent to satisfying the conditions from the previous slide. So sometimes I still think of these instead. Sometimes, knowing things like square decreasing has been useful for me to work with these objects. And so now that we sort of have at least seen what a locally integral ipo-semigroup is in terms of its definition, we can talk about what it was that we've been trying to do, which was, first off, find some kind of decomposition theorem for locally integral ipo-semigroups, by which I mean we want to look at these locally integral things and we want to break them down, preferably into smaller subalgebras in a way where if we put those subalgebras back together, we can recover the original structure. That's somewhat of a big goal, lots of steps involved. The first thing we do to go reach that end is we try to partition each locally integral ipo-semigroup into integral subalgebras. So we picked things that we then called locally integral because we wanted them to look, in a sense, if we zoomed in, like integral things. So we're hoping we can then use that concept, break this apart into a bunch of integral things and say, well, actually, locally integral ipo-semigroups were a bunch of integral things all stacked up in a trench coat. So our goal, or really what we did, is we wanted to break things into equivalence classes, and we wanted to be able to index these on what's called positive elements. So positive elements are exactly those elements where x is smaller than p times x. So multiplying by them, like I've been saying, makes things bigger. And then we could dually define a set A tilde that has all of the tildes of the positive elements. And these positive elements are particularly nice because, for one thing, they're all central. We love central things. And second off, if we look at what the set of positive elements of an locally integral ipo-semigroup is, the positive elements turn out to be exactly and only the local identities. So every local identity is positive and nothing else is. And then dually to that, the set A tilde is only the zeros. All of the zeros are in A tilde, nothing else is. And then we get nicely that 0 is stacked beneath 1x, and we know that x is going to be in there somewhere. So we're starting to see sort of a structure where things are bounded between 1x and 0x, or at least we hope that's what we're seeing. So we can define an equivalence relation using these positive elements, these local identities. And we can say x is going to be equivalent to y if they have the same local identity, if 1x is equal to 1y. This is pretty easy to see. It's an equivalence relation because it's definitely going to be reflexive, it's definitely going to be symmetric. And since the thing we're working with on the other side of that if and only if is equality, it's also going to be transitive. So we can have this equivalence relation and we can break apart the corresponding equivalence classes. And we can call these equivalence classes AX, and they'll be the set of all the elements that have the same local identity as X. And these turn out to be nice. These are going to be what we're looking for, the components that we break apart into. Because if we first discover that they happen to be subalgebras of the big structure A, when we look at them, we see they're closed under the involutive negation. So if X is in the equivalence class, then tilde X is as well, as is minus X. They're closed under the multiplication operation. They're closed under all existing non-empty joins and non-empty meets. So they're really nice. And if we look at, we can also see with just a little bit of effort that the top element of each AX is going to be that element 1x. So they're also integral, which is nice. And so all we've got to do now, and I say all we've got to do, this is a small lie, but the next thing we want to do is find some kind of canonical representative for the equivalence classes, AX. Some way of indexing these equivalence classes. And what we discover is that if we look at one of these equivalence classes, AX, well, the only positive element that appears in AX is going to be that local identity 1x. There will be no other positive elements in there. And similarly, there will be no other like tilde elements other than 0x. So that means if we want, we can pick that 1x as the representative of the equivalence class, which means that the set of all of these AXs is actually just the same thing as the set indexed over the positive elements. So we have a bunch of integral ipo-monoids, as it turns out, which are these APs, which we define as the set AP. And then all of the operations and relations just restricted to that subset. These turn out to be integral ipo-monoids. So we can take any locally integral ipo-semigroup, break it down via this equivalence relation, and go, okay, all of the pieces are integral ipo-monoids. But we'd want to do more than just like break it down and go, hooray, we're done. Because A is more than just a disjoint union of all of these things. These components interact with each other in very specific ways. As just one example, if you multiply an element X, which is in the pth components, and an element Y, which is in the qth components, their products will be in the component that you get by multiplying the positive element P with the positive element Q, which gives you positive elements. So if we just say disjoint union and we're done, we'll miss this sort of thing. This just will not happen. So what we want to figure out is what mathematical construction will describe a way to take these, break things down into these integral components and then put them back together and get what we started with. I will spoil the answer. The answer is Płonka sums. And for those who may not be familiar, I will briefly go through and tell you what that means for us here. And we're going to begin with a join semilattice. We'll call it I because it's going to be an index set. And that's just a set with an associative, commutative, and idempotent operation attached, which lets us define an order on it, a partial order. So, and then we also want a family of algebras called A, and we want those algebras to all be indexed on the set I. Then the third ingredient is what's called a compatible family of homomorphisms. And what do I mean by that? We'll say we've got a family, capital phi, index phi I, so that we have phi ij goes from the algebra AI to the algebra AJ whenever I is less than J in our index set. We call this family compatible if it composes nicely. If phi from I to I is just the identity on the ith components, and if phi ik is equal to the composition of phi jk and phi ij. So in total, put this all together, and a semilattice directed system is going to be a tuple with a joined semilattice I, a family of algebras of the same type A, and a compatible family of homomorphisms between them. So these are all the ingredients we need to put together what's called a Płonka sum. And the Płonka sum is just going to be an algebra that's on the disjoint union of all of the universes of these AIs. And then we've got to define operations on this thing. So we take any non-constant in-array function symbol, say sigma, and we take any elements A1, element in algebra AI1, all the way up to AN in algebra AIN. And we want to say what sigma of A1 to AN is. Well, we do this by taking all of those indices, I1 to IN, taking their join, let's call that J, and now we bring each element through the phi map up into the jth component and just perform whatever the operation sigma was there. So we bring everything into the same components, perform the operation using the operation that already exists on that algebra. And we go through and we do this for every function symbol that appears in the signature of this type of algebra. And in the end, we get something on the same signature, and it will satisfy all regular equations that hold in every algebra in the family, which is to say an equation is regular if it's got the same variables on both the left and right-hand sides of the equalities. So it'll satisfy all equations that have the same variables on both sides of the equality. That's a Płonka sum.
Wait, all, okay, can I ask about that again? All equations that hold on, okay. You're going to explain that, or why that is true?
I am just leaving that with you for now. Off the top of my head, I do not know how to prove this is true, but a few weeks ago, Stefano Bonzio gave a talk and did discuss this in some details. He with a couple co-authors has a great book on Płonka sum. Thanks.
Yeah, I remember that he was here, yeah, and okay. So it's in his book, you're saying?
It should be, yeah.
Yeah.
So we've introduced Płonka sums, we've introduced locally integral ipo-semigroups, talked about how to break them down into integral components. And that means that we might want to take a Płonka sum of integral components. So the first thing we need in order to be able to do that is a joined semilattice to index over. And luckily, we were already indexing over positive elements, and by great good fortune, the positive elements of a locally integral ipo-semigroup do form a joined semilattice whose order coincides with the order on the whole big algebra. So we've got a joined semilattice, and that means we can then define the family of morphisms between these algebras. So if we got two positive elements, P and Q, with P being smaller than Q, we need to have a map between them, call it phi PQ, from algebra AP to algebra AQ. We define this by phi PQ of X is equal to Q times X. And we do this for, all positive elements, P and Q, P smaller than Q. And that's our family. This will turn out to be compatible. This will turn out to be exactly what we're looking for. Which is to say, if we've got a locally integral ipo-semigroup, then its associated family of these phi PQs defined by phi PQ of X is QX is compatible, but it's just a compatible family of monoid homomorphisms. It's not going to preserve the involutions. And that's by choice. We only want this to be a monoid homomorphism. And it will be indexed by the order of the joined semilattice. So this gives us, taken all together, a semilattice directed system consisting of the positive elements, the integral components, and this family of morphisms that we've just defined. That means we can take the Płonka sum of this family of algebras with the monoid homomorphisms and put that all together. But we only took the morphisms to be monoid morphisms, which means that the Płonka sum we get out is just the semigroup reduct of A. And we'd like to be able to recover the rest of A. So we need to be able to recover tilde and minus, and we need to be able to recover the order. Luckily, tilde and minus are really easy. They're always computed just within their own components. So we just say tilde with respect to this S of X is just going to be the same thing as taking the tilde normally in whatever component X comes from. Same for the minus. Then we have to define the order. And this, I believe, is largely due to Jose. It's a pretty nice little construction. It turns out that X being less than or equal to Y is exactly the same thing for X in the P component and Y in the Q component as saying X times tilde Y is equal to the 0 of the component that that product winds up in. This will come from rotation applied the right way and the local identities acting as identities on certain elements. So if we define the partial order in this way, it will indeed be a partial order. And not only that, when we take this Płonka sum plus this order plus this tilde and this minus, we get back exactly the algebra we started with A. So the moral of the story here is that we can take any locally integral ipo-semigroup and we can break it down into its integral components, and then we can recover it back by building up the Płonka sum of the semigroup reduct of its integral components and defining the remaining operations and relations in the right way. And this here is sort of an example of what's done. On the left, we have our joined semilattice that we're indexing over. It's just a diamond. And then we have our components in sort of from left to right, increasing order positive elements. And we're able to glue them together by gluing together the positive elements in the order of the semigroup and gluing together the negative elements, or not negative elements, but the tildes of the positive elements in the reverse order, sticking everything together so that when we're done, each component is sort of nested in the component above it. So the component of A1 will, in the order, be nested inside the component of AP, and it will be nested inside the component of AQ because it's smaller than both of those. And we take those components and set them inside the join of AP and AQ. This is a pretty generic looking example for if we're just trying to join things, glue things together over a diamond. So that's great. We have a decomposition result. We know how to recover the algebra we started with. But we also came up with a construction when we were doing this. We have if we have some semilattice directed system and some family of integral IPO, which consists of a family of integral ipo-monoids and monoid morphisms between them, we can glue them together the same way we did with the previous slide and define all the operations in just the analogous way. And then we might ask ourselves, we've glued together a bunch of arbitrary integral ipo-monoids, and we've called this, the integral of over phi of AP. We call this, just like the gluing or the semilattice directed gluing, something like this. And we know if we started with an locally integral ipo-semigroup, we got one back. But if we just start with something arbitrary, when are we still going to get an ipo-semigroup out of this? This is the next question we want to answer, a construction that will work. And so there are a bunch of conditions that we end up having to impose, and by a bunch I mean 4, which is not actually that many, that we have to impose on the family of morphisms to make this work. So the first one we came across was this one we call zero avoidance, which is that the maps phi pq, well, phi pq of 0p is equal to 0q if and only if p equals q. So unless the map is the identity you never map anything to the zero of the next component. This ensures that the positive elements and their negations behave, properly, should probably be in quotes there, but in the way that guarantees that the positive elements are only the local identities and the tilde elements are only the tilde of those. The second condition that we came across was that we needed to make sure that our gluing was going to satisfy the rotation property, or we could have equivalently gone for the residuation property because we're going to want that double negation anyway. And this leads us to what we call balance. The balance condition says that if you apply tilde, then a phi map, then a minus, so this is the same as swapping the tilde and the minus. If you do the minus, then the phi map, then the tilde. And if that happens, if we have that all of these maps are balanced, then we will get that the involutions are antitone, they're order reversing, which is something that we require. And we will also get that we satisfy rotation. So now we've fixed the positive elements. The set of positive elements is going to be what we want it to be. And we have order reversal and rotation. There's still a few more things we need to make sure happens. For one, we need this relation to be, we know we can figure out pretty easily, it will be reflexive pretty much no matter what we do. But we need the relation to be transitive and anti-symmetric. So we'll try to handle transitivity, which is not a difficult condition to express. We just say x is smaller than y and y is smaller than z implies x is smaller than z. But this turns out not to be the best characterization to use on our system here. What we end up doing instead is that in the presence of zero avoidance and balance, the two conditions that we just came up with, we have two other conditions called mon and lax, which turn out to be exactly equivalent to transitivity. And mon is, I think the inspiration for the name probably came from monotonicity, but it's the idea that if A and B were related in the same component, A is smaller than B, you map them up to a higher component and the image of A is still smaller than the image of B. And then lax is this weird one. You've got a setup where you're sort of in a V in the semilattice. You've got P and it's below two things, Q and R. And you want applying phi PQ and then taking the tilde to be less than or equal to applying the tilde and then taking phi PR. It turns out mon and lax in conjunction with zero avoidance and balance will give us transitivity. And the good news is that we do not have to separately handle anti-symmetry, which is the last poset condition that we really needed. It comes for free with the other conditions. In fact, if we satisfy just zero avoidance, balance, and lax, then we can guarantee that the order that comes from our gluing is going to be anti-symmetric. So in summary, if we satisfy zero avoidance, balance, monotonicity, mon and lax, then we get a reflexive, transitive, and anti-symmetric relation. We get an associative binary operation, which comes from the Płonka sum. And we get a gluing that satisfies double negation and rotation. So if we're paying attention, that is exactly the same thing as ending up with a locally integral ipo-semigroup. So we can now go both ways. We have a complete characterization of what these locally integral ipo-semigroups look like. They're locally integral ipo-semigroups. If and only if there is a semilattice directed system of integral ipo-monoids that satisfies those four conditions that we can glue together and it's equal to the structure that we were looking at. And we can also determine exactly when we'll have an identity. A will have a global identity if and only if that semilattice D has a minimum element. And then that minimum element, or the one indexed by it, will be the global identity. And so if we want, we can take any family we want of non-trivial integral ipo-monoids, and then we can construct a locally integral ipo-semigroup that has those components. You just say our semilattice order is going to be a chain, and if we want it to have an identity, we just say, well, we'll pick one of these components to be the bottom one. And then you define your maps by mapping everything to the top elements of each component. This will work out. And now you've got a locally integral ipo-semigroup that has got the components that you wanted it to have. So now we specialize a little because I want to go back to lattices. We've got a nice characterization of partially ordered stuff, but this does not describe when we get a lattice. So this is what I'm aiming towards as we go through here, and I will try to get through this relatively quickly because looking at the time, it seems like I haven't got that much time left. And the first thing we zoom in on, just to sort of help us on our way, is what happens if we specialize to idempotent locally integral things. Well, what will happen then is that every single integral component will have to be Boolean. So all locally integral ipo-semigroups that are idempotent are composed as sums of Boolean algebras. Boolean algebras are nice. This is what we've zoomed in on. They're much easier to work with than just some random other integral ipo-monoid. And then since Boolean algebras are commutative, then any sum of them is going to be commutative and idempotent as well. And that means that the operation will be a semilattice operation. So an idempotent ipo-semigroup, we call it an ipo-semilattice. And if that ipo-semilattice, if the partial order was actually a lattice order the whole time, we call it an il-semilattice for lattice-ordered semilattice. And one thing that's really nice about these idempotent semigroups or these ipo-semilattices is that you can define another order on. We call it the multiplicative order because it was induced by the multiplication. We denote it with that square less than or equal to, and we define it exactly by x is square under y if and only if x times y is equal to x. So it gives us a meet semilattice. One thing to note here is if we throw in a unit, then we end up exactly with commutative, idempotent, involutive, residuated posets, because the only difference there was that we required a unit. And if we were lattice ordered, then we get exactly the variety of commutative, idempotent, involutive, residuated lattices. Has been studied in a very similar context very well. In fact, the structure of all of the finite commutative, idempotent, involutive, residuated lattices, which is a mouthful and which is why I usually prefer to say unital IL semilattices, has been given in a 2021 paper by my advisor here, as well as Tuyt and Diego Valota. And it's by means of this construction, which I'm just going to quickly try to list out here so that I can try to generalize it to our non-idempotent setting. And we require two disjoint unital IL semilattices, so just any two members of that variety. I say any two, this is not quite true. We need to be able to pick an element A in them. And we want that element to be below the unit, but not below the 0. And then we just pick any element that's below the 1. And we take some function theta that maps between the multiplicative upset of the element A and the multiplicative downset of the element B. We need that to be a bijection. We need it to preserve the fusion. We need it to preserve the join. And we need this weird little condition that's actually very similar to our 0 avoidance condition on our sort of Płonka sum construction. The 0b is equal to theta of A join 0a. If we have all of these things, we can define a construction. We put these two structures together, A and B. We want something on the universe A union B, and we define a lattice from it. So this is different from our Płonka sum construction in that we could only out of hand guarantee we were going to get something partially ordered. We know we're going to still get a lattice if we use this construction. We can construct all of the operations as listed on that slide there, which I will not go into in great detail, but it's essentially just applying the theta maps to move everything into the right component and then performing the operations there. And what this looks like, if we want to see more of a picture of it, this is often easier to express in the multiplicative order. We've got, if we look over on the left in the multiplicative order, we've got sort of this small chain of Boolean squares, and then we're gluing to it a square that's already been glued to a cube. And so we can see that map, those dotted lines between them are exactly what that theta map's gonna be. And then this is much harder to see if we rewrite this in the lattice order. This is essentially what's going on. We take those two things together, we smush them together along this theta map, which we were able to define, which is a bijection on some filters and ideals. And we get a lattice back out, and we can express the lattice order as so on the slide. So this is just an example here of how if we glue together, according to the construction on the previous slide, a pair of unidal IL semilattices will again give us a unidal IL semilattice. So this is nice. We can make more lattices, and this is a very iterative construction. So we could start, if we wanted, just Boolean components and build up from there, gluing again and again. My goal, which is most of what I've been doing this term, is to determine a construction in a very similar way, generalize the one we've just seen, by which a gluing of now not necessarily idempotent, locally integral ipo-monoids is again going to be lattice ordered. So you'll note I said monoids because it makes things easier, and I was able to figure out what I should do there. I did require we have an identity. And our sub goal of this is, well, if we're just trying to generalize the construction from before, what we need to do is, a couple slides ago, we had a long list of ingredients that we needed to have in order to make this construction work. I'd like to know what the ingredients are to generalize this in the non-idempotent case. To do that, we go back to this 2009 paper, again by my advisor, and talk about complemented elements. And we'll specialize to the case of integral IL monoids right now, because that's what we're looking at most often. And we'll define a complemented element there. And we'll say it's complemented, an element C is complemented if there exists some other C prime, so that C and C prime join to 1 and meet to 0. In the integral involutive case, this will turn out to be that C prime will have to be the tilde of C, which will be equal to the minus of C. Then we can define the Boolean center as the set of all of these complemented elements of A, which is justifiably named because if we're in an integral IL monoid, then the Boolean center is going to be a Boolean sublattice of central idempotent elements. So it will turn out that if you looked at only the complemented elements of your integral IL monoid, you could pluck that out as a Boolean algebra. But we aren't working with integral things, we're working with locally integral things. So I will then define what's called a locally complemented element. So now we just have a locally integral IL monoid, and we've still got an element C. And we'll say it's in the P component of its decomposition. Then we say it's locally complemented if it was complemented in its integral component. And the Boolean center will still just say is going to be the set of all of those locally complemented elements. So what we can notice is that if the Boolean center is a sub-IL monoid of A, if everything of all of those homomorphisms, the phi morphisms, act nicely with respect to the Boolean center, then we get a sub-unidal IL semilattice sitting right inside our locally integral IL monoid, which means we're very nearly in the setup of the 2021 paper that only dealt with unidal IL semilattices, because we've got one of those sitting inside it, and then we've just got some extra elements. But there's another little hitch, which is that without idempotence, we don't have access to that multiplicative semilattice order. And this is a little issue because we were using that square less than in order to figure out where that bijection theta maps to. The bijection theta was mapping to a between an upset on the multiplicative order and a downset on the multiplicative order. So without the multiplicative order, what do you do? The workaround is, suppose we've got I've written an IL semilattice there, but I do not want an IL semilattice. That is a typo that I've missed. We just want that to be a locally integral IL monoid. And we can define an operation on it. We'll call it the square meet because it's going to correspond to the square order. And that'll be the Płonka sum meet. And what I mean by that is that if we take two elements in the P component and the Q component, we bring them up to the component of their join, and then we perform a meet there. And this will let us define an order on that. We'll define the order in more or less the same way we did before, except we'll now say the x is square under y if x square meet y is equal to x. So this is our workaround. This is what we use. And now we have a revised ingredient list, which is fairly similar to the one we had the first time around. But we have some extra requirements. This time we just want A and B to be disjoint, locally integral IL monoids, so we don't require idempotence. But we would like the Boolean centers to be unidal IL semilattices sitting inside them. I'm not entirely sure whether this is always true or not. I suspect not, which is why I'm forcing it to be there. But I think it's I say very nearly true. This is not really a technical term, but the Boolean centers are almost nice, is my suspicion. But in any case, we require the Boolean centers to be nice. We need them to be unidal IL semilattices for the construction that I've done. And then we require an element A and an element B like we did before, but we want to make sure they're in the Boolean centers. We want them to be locally complemented. This was hidden before in the Boolean case because everything was locally complemented. But this is what we require, and we still want that the element A is less than the unit of A, but not less than the 0 of A, and we still want that the element B is less than the unit of B. Then we define a function theta again. It's going to need to be fusion and join preserving bijection. And we need it to map between this, the Płonka meet upset of the element A and the Płonka meet downset of the element B. So this is entirely analogous to the previous construction, but instead of using the multiplicative order, we use the new square order that we've defined. And then as long as there's the bijection, it preserves the fusion, it preserves the join, and we have that 0b is equal to theta join, theta of A join 0a, just as before. We can then define a gluing in an exactly analogous way. I will still not go through the excruciating details, but I will note that it's almost entirely analogous, except that everywhere that we had a multiplication with a locally complemented elements the first time around, we replaced that with a square meet, and we also have to handle that multiplication may no longer be commutative. But other than that, it's extraordinarily analogous to what we did the first time around, and we can also dually define the meet from the join. And once we do this, we get to the main result of what I've been doing this term, which is we now have a way to glue IL monoids to get more larger IL monoids. If we have two locally integral IL monoids whose Boolean centers are unidal IL semilattices, and there's a bijection theta between the subsets of A and B that we've defined on the last couple slides, then that gluing with the operations we defined on the last slide will turn out to be a locally integral IL monoid. So this is great. This is, I think, probably where I should stop. I think we're about out of time.
I guess.
But if anyone wants to know anything about the details of how this is done, because it's done by means of proving things with a Płonka sum decomposition, I am happy to go over the details at any time. So thank you very much.
Okay.